Welcome back. Okay, we are in the fourth lecture in our series on complex analysis, complex variables, complex functions. And today I'm going to introduce one of the most important complex functions, the complex logarithm. So I'm going to be very specific that this is the complex logarithm because it is actually different than the real valued logarithm. And this is where we're going to start seeing how strange things can be in the complex function, the complex plane. So the logarithm, we found that the complex exponential function was essentially very similar to the real valued exponential. It had a convergent Taylor series. It was analytic everywhere. I haven't told you exactly what analytic means, but it means that it has a convergent Taylor series everywhere. The complex logarithm is a little bit more complex of a creature. And yeah, so this whole lecture is going to be all about this function, how to derive it, what are its properties, and I'll give you some hint about how we're going to use it in the future. So kind of maybe I'll give away some of the punchline. This is actually going to be a function that has infinitely many values for a given input z. There are infinitely many complex logarithms of z, and the fact that this is an infinite valued function, it's going to be that's a very important property when we later use this for things like the inverse Laplace transform or taking the square root of -i, things that we haven't done yet that we will do in future lectures. Now that was too much teaser. I'm just going to jump right in. So the complex logarithm, and I'm going to use two different colors here, I hope. So we're going to let z equals x plus iy. This is our input variable. And we're going to let our output variable w equal u plus iv. Okay, and we're going to say essentially that w is going to equal the logarithm of my z variable here. Okay, so we're going to take the logarithm of z, and the output of that logarithm is going to be this w variable. And we're specifically going to define this complex logarithm so that it is the inverse of the complex exponential. So if this is true, then we expect that the exponential of w is going to equal z. So z should equal the complex exponential e to the power w. And so we're going to use this kind of, remember, the logarithm and the exponential are inverse functions of each other for real valued arguments. And so for complex valued arguments, we are also going to expect that these are inverse as well. So this is called an inverse pair. And this is really common, right? Like multiplication and division are an inverse pair. Addition and subtraction are an inverse pair. The Fourier transform and the inverse Fourier transform are an inverse pair. Log and exponential are an inverse pair. And so we're going to use this to derive what we mean by the logarithm of z. And specifically, notice that I'm using a capital L logarithm. This is a very subtle thing that mathematicians do to specify that we're talking about logs of a complex variable z. That's the capital logarithm, the kind of complex logarithm. Good. So I'm going to use this relationship to derive what we mean by log of z. In particular, how do u and v depend on x and y, and vice versa. And then we're going to derive some interesting properties about these weird functions u and v, which are the logarithm of z. Good. And so I think I'm going to go back and forth a little bit between this Cartesian representation in terms of the real and the imaginary part, and also in terms of the polar representation in terms of re to the I theta, re to the I theta. Okay, so this sometimes it's going to be easier to think about it in terms of this expression here. But we essentially have that z equals e to the w. Maybe I'll just stick with pink here. So this equals e to the u plus iv. And remember, whenever you have e to the a plus b, it's e to the a times e to the b. So this equals e to the u times e to the iv. That's e to the u times e to the iv. And remember, u is real and v is also real. U is real and iv is imaginary. So e to the u, this is a real valued exponential. This is a real number. And e to the iv, that's just cos v plus I sine v. Okay, so we're going to use that. We're going to use that now. So this equals, let's say, e to the u power. I should just keep this on hand. Times, we're going to say this is cosine of v plus I sine of v. Good. This is all, essentially just from this definition that the logarithm has to be the inverse of the exponential. So I took my z and w, and I just flipped them, and now I'm solving for what are my z terms in terms of my w terms. And here, this is actually where I could probably much more easily just use the fact that if I represent this, in terms of the polar coordinates of z, r e to the I theta, it's pretty clear that r equals e to the u and theta equals v. That's pretty obvious that the only way that these can equal each other, this is a real number, e to the u has to equal r, and e to the iv has to equal e to the I theta. So that's certainly true here. And so I think I'm actually just going to write down this answer. I'm just going to say u equals, or e to the u equals r. So u has to equal the logarithm of r. And notice I'm using lowercase l logarithm here because r is a real number. It's not a complex number. R is a radius. It's a real number. This is a real valued logarithm. And this u term here is just the real valued logarithm of the radius of z. Okay, so log of z, the real part of that, is going to be the log of the radius of z. And the imaginary part here, v equals theta. V equals theta. Okay, so that's like pretty easy actually. We've essentially just shown that for these two to be inverses of each other, u, the real part of my log of z, has to equal log of the radius of z, and v, the imaginary part of my log of z, has to be the phase angle of my variable z. This is certainly true. And I'm going to maybe write these down using an alternative notation that you're very frequently going to see. So this is also the log of the norm or the absolute value of z. So remember, the absolute value of z is its length or its radius r. This is just notation. This is definitional that norm of z equals r. Okay. Literally, if you took x squared plus y squared, it would equal r squared. That's what I mean by the length of that z. And similarly, oftentimes theta is defined, I'm just going to say defined, as the phase angle, the angle of that variable z. Okay, so literally, if I was in the complex plane, this z would have a radius, and the phase angle of z equals theta. So r equals the norm of z, theta equals the phase angle of z. But this is essentially true. This is absolutely true for u and v. U and v equal these quantities in terms of my original variable z that I'm taking the logarithm of. But here's where it gets super weird. Okay, what's super weird is that I could add, let me pick a color, I could add plus 2 pi n here, and nothing would change. Because if I take my variable z that is at an angle theta, and I add another 2 pi to it, I'm right back where I started. Cosine of theta plus 2 pi is equal to cosine of theta. Sine of theta plus 2 pi is equal to sine of theta. And I can do that for any whole number n of rotations around in this complex plane. So that's really, really interesting, is that when I take the logarithm of z, this w quantity has to be the inverse. When I exponentiate w, I need to get z back. And for any of these, I should be more careful. If I add plus 2 pi n here, if I add 2 pi n to this theta, when I exponentiate that, when I take, and I plug that into here for the v, it'll loop back around and it'll give me r e to the I theta. These are going to be equal quantities. I could say this 10 more times more slowly, but what I'm going to do is I'm going to draw you a picture, because it's going to make all the sense in the world when I actually draw you a picture of this. But what this means morally is that for a single number z, for a number z, which is defined as, r e to the I theta, there are actually infinitely many solutions to the complex logarithm of that z. So this is true for all integer n. N could equal 1, 2, 3, 4. It could equal -1, -2, -3, -4. What that means is that the same, if I take this z and I add 2 pi or 4 pi or 6 pi or 8 pi, or if I subtract 2 pi or 4 pi and so on and so forth, I get the same number afterwards. That's what we're seeing here, is this kind of, because you can think of theta as rotating in the complex plane, when I add integers of 2 pi to that phase angle, I get back right where I started. Okay, good. So I'm going to draw you a picture, and then I'm going to write down what this logarithm is. So let's pick, and again, I'm going to do this color-coded. So I'm going to have 2 different complex planes. This is kind of my input complex planes, where this is C, this is the real, X, and this is an imaginary Y. And then once we take the logarithm, we're going to, this is, let's say, my z plane, and then here we're going to be talking about the w plane, where similarly the imaginary part is v and the real part is u, and again this is a complex plane. And what we're going to be doing is we're going to be saying that, if I go from z to w, that's the log function takes me from z to w, and the exponential function e to the w equals z, and log of z equals w. So w equals log of z, z equals e to the w. And essentially what this function log and e do is it maps me from the z plane to the w plane and back and forth. Okay? And so I'm going to draw my z vector in my z plane, and I'm going to draw my w vector in my w plane, and we're going to understand kind of pictorially what this relationship means and what it means for this to be multi-valued. So in the z plane, I have my, my z here, and this has a radius and a theta. And I think what I'm going to do is I'm actually going to call this the principal theta. This is theta p, because for any number z that you pick, any point in this plane, any x and y, that z could be defined as r e to the I theta p. But I could also add 2 pi or 4 pi or 6 pi or 8 pi. And those are all equal to the exact same point z. Because if I go around 2 pi, I come back to the same place. If I go around 4 pi, I come back to the same place. So technically, this could be, plus 2 pi n. I could go around 2 pi any integer number of times, and I'm still at exactly that point z. So there are infinitely many angles I can use to represent that angle of z. And the principal one is usually defined to be between 0 and 2 pi. So this is a number between 0 and 2 pi, and of course I can add 2 pi as many times as I like, and I get back to the same point. Now, the complex logarithm, we know that the real part of my complex logarithm, the u part, so let's say the real part here, the real part of w equals u, and that equals log of my radius. So this is log of the radius. So this is a line, which is literally the real part of w is log of radius, log of this radius. And the phase angle of w could be any one of infinitely many values. It could be theta p. So this point here is theta p. But it could also be theta p plus 2 pi. That is equally valid. That's also z. It could be theta p plus 4 pi, theta p plus 4 pi, and theta p plus 6 pi, plus 8 pi, plus 10 pi, 12, and so on and so forth, minus 2 pi, minus 4 pi. So there are infinitely many points in this w plane that when I exponentiate them, when I take e to all of these blue dots, when I take e to any of those, it'll map me exactly to this value z. Okay, so that's really interesting. The log of this point z has infinitely many values that are all equally valid. And so I think what I want to do is I want to write down the actual formula here. So the complex logarithm of z, capital log of z, equals a real part, and that real part is log of the radius r, which I'm going to say is log of the length of z, plus I times this principal angle, the angle between 0 and 2 pi that uniquely identifies that point z, plus any integer multiple of 2 pi n. This is for all integer n. This is how the complex logarithm is defined. And this is really, really important. So the complex logarithm is an infinite valued function. For every point z, there are infinitely many logarithms of z. If I choose n equals 0, this is called the principal logarithm. That's kind of the standard logarithm. Okay? And this might seem weird, but that's not the weirdest thing you've ever seen in math. Remember, if I take the square root of 9, that's also a multi-valued function. We know that there are two values for the square root of 9, 3 and negative 3. There are, two values for the square root of negative 1, I and minus I. This is no different. There are just infinitely many solutions of logarithm z for every integer power, for every integer n here. And teaser, we're actually going to use this formula to compute things like the square root of negative I. What is that equal to? We're going to use this formula to compute the square root of negative I. Or we could compute the cubed root of positive I. What does that equal? And I claim that the square root is going to have 2 solutions. The cubed root is going to have 3 solutions. And so on and so forth. You can take things like the pith root of I. That's going to have infinitely many solutions, just like the complex logarithm. So those are things I'm going to show you in the next lecture, but it's not that weird that you have a function with infinitely many values. We already are used to multi-valued functions like the square root of 9 has 2 values that are equally valid here. Good. Okay, so I want to recap a little bit because I think that this can be confusing, and I just want, now that you've seen it all, I'm going to slow down for a minute and we're just going to go through the key steps so that you can see where this idea of multi-valued logarithm comes from. Okay? So we are defining the logarithm of a complex input z. We're calling it w. That's the log of z. And we expect that the log of z is the inverse of the exponential function. So if w is the log of z, then e to the w has to equal z. And if I take e to, this all really relies on the fact that if I take e to the w plus 2 pi I is equal to, basically I'm just saying that's equal to e to the w. I'll come back to this in a minute. So we expand w in terms of its real and imaginary part, and we expand z in terms of its radius and phase angle. And through some algebra, essentially just plugging things in, we find that u has to equal the radius and v has to equal the phase angle theta. Okay, that's a very valid solution. That's the principal solution. But what we also find is that if we add 2 pi to this w, it is still a solution e to the w equals z. That's still the inverse of the logarithm. And that's true for 2 pi I, 4 pi I, 6 pi I, 8 pi, and so on and so forth, for all integer multiples of 2 pi I that I can add to this thing. And why is that the case? That is the case because if I add 2 pi to this theta, this cosine theta and sine theta don't change. Because if I define z as r e to the I theta, I could equally well define it as r e to the I theta plus 2 pi, plus 4 pi, plus 6 pi. Okay, so that's why this complex logarithm is multi-valued. It's because I can rotate this around any multiple of 2 pi, and I have the same value z. This is going to really require you to sit quietly and think about why this is true and how this is true. I think this picture really helps me think about it. But this is one of the most fundamental properties in complex analysis, is that some functions are multi-valued. Like the square root function has 2 values, the cube root function has 3 values, the logarithm has infinitely many values. Good. And so there is this notion of something called a branch cut in complex analysis. I'm just going to write this down. A branch. So essentially a branch of a multi-valued function, like the logarithm, a multi-valued function, f of z. Remember, f of z, my logarithm of z, is multi-valued. It has all of these values. A branch of a multi-valued function z is essentially is a single valued function, we'll call it f of z, which is essentially defined on a region. I'm going to use some math speak. A region D, which is a subset of the complex plane, that essentially coincides, that is the same as f of z on that branch. I'm going to draw you a picture that coincides with f of z on that branch. So let me draw you a picture because this is a little bit confusing. So the u component of log of z is single valued. There is only one number for the log of that radius, and that never changes. I can't add 2 pi to that. I can't change that. The real part, u, is single valued. It's the imaginary part, the v component of w, that's multi-valued. And so if I take and I literally plot this function, there's kind of a cool way you can plot this where this is x, and this is y, this is the real valued part of z, and this is the imaginary valued part of z. And I plot the imaginary part of log of z. So kind of, this equals v, right? This is the v part of this, the imaginary part of my logarithm of x. What we find is that this thing starts off at some value, let's say it starts off at 0. And as I go around in this complex plane, as I clock this thing around 2 pi, 4 pi, 6 pi, 8 pi, this essentially winds up almost like a spiral staircase in this phase angle. So this is kind of a weird picture. But what this means is that if I take my complex plane here, and I go around in one circle, I add 2 pi to this principal angle, I have added 2 pi. So if I go around one circle in the xy, the z plane, then I have essentially added 2 pi I to the phase angle of v. And if I go around a second time, 4 pi, then I go around and I've added another, this is plus another 2 pi. So this is, another 2 pi I. And each of these levels of this kind of spiral staircase of v is called a branch. This is the principal branch, but there are other branches I could take of this multi-valued function. And generally speaking, we have some rules, like we would pick the principal branch to be the one between like minus pi and pi, or 0 to 2 pi. Just like, when you define a number in polar coordinates, you define its principal theta as the theta between either negative pi and pi, or 0 and 2 pi. It's exactly the same thing here. And this is really, really weird, because if I do the following, I'm gonna give you the punchline because I can't help it. This is like where this is all going, is that if I take my, my z plane and I integrate around a closed loop, let's call this a contour C. If I integrate around a closed contour C that includes the origin of log of z dz, this is going to equal 2 pi I. If I go around in a full circle, if I start here and I go around a full circle of z, I have added 2 pi I of phase to the logarithm of z. And so the integral of that over that closed circuit equals 2 pi I. This is the basis of one of the most important integral theorems in all of mathematics, called the Cauchy integral formula. This is how we're going to solve for the inverse Laplace transform. It's a super, super useful property that with these multi-valued functions, if I integrate a closed orbit and kind of go up one of these branches, I will add a phase angle of 2 pi I through that integral. So this is a really important property. I'm going to talk a lot more about what these complex integrals in the complex plane mean. So if this was a little confusing, I'm going to have whole lectures on what it means to integrate in the complex plane around these closed orbits. But I just want to point out that the fact that this is a multi-valued function means that if I go around in a circle, I add 2 pi I to my phase angle. If I go around in another circle, I add another 2 pi I, so I'm up to 4 pi. And I can keep doing that if I keep integrating around these closed orbits. Okay, so complex logarithm, very, very important and special function. It is the inverse of the complex exponential. And because of the way that we define these complex variables in polar coordinates, where I can add 2 pi, 4 pi, 6 pi, 8 pi, and so on to the angle, this logarithm is infinite valued. We're going to use this for things like the inverse Laplace transform. We're going to use this to define things like the square root of negative I and the cubed root of I and things like that. So that's all coming up. Stay tuned. Thank you.